So we're going to look at limits with graphs, rational functions, and looking at and recalling limits, recalling where graphs, rational functions have asymptotes. Okay, so there's different types of asymptotes. You can have a vertical asymptote. So that's going to occur in values which set our denominator equals 0, but not our numerator. So vertical asymptotes. Now that we know rules or terminology of limits, basically, as you're approaching some value c of your function f of x, this is either going to equal positive infinity or it's going to equal negative infinity. So as you're approaching your value x equals c, that graph is either going to be shooting upwards or downwards and growing continually. So this is one possibility. And in this case, this would be, if I was looking at it coming in on the right, this would be going to positive infinity. It's possible as we look at the limit as x is coming in on the left. Sorry, I'm totally wrong. That is a left, as x is approaching c on the left. This would be going up to positive infinity. And the limit as x is approaching c on the right, the limit is going to be going down to negative infinity. If you look at this graph, though, notice that as x is going to infinity, looks like this graph would be hugging our x-axis. And so, and if you're looking at the limit as x is going to negative infinity, it also looks like it's hugging the x-axis. And so here we have a horizontal asymptotes in this case. So that's going to occur when the limit as x approaching some value, or not some value, infinity of our function. I call this f of x. F of x, this is going to equal some value k. In our case up here is the limit as x approaches positive infinity of f of x. This is getting closer and closer to the x-axis 0. Same idea, the limit as x is approaching negative infinity of f of x. This is getting closer and closer to y equals 0. Then we can also have what are slant or oblique asymptotes. Let's not worry about that right this second. Okay, so vertical asymptotes. Again, they occur at values that set the denominator equals 0. But not also the numerator. Okay, so we saw that when that happens, they set it both. That's actually a hole in the graph, and we talked about that. And we could actually make that a removable hole by defining it at some value. So vertical asymptotes are only one that sets the denominator equals 0. Horizontal asymptotes, this has to do with the degree of the numerator and the denominator. Okay, so you're going to look at the degree. And the numerator and denominator. So 3 things could happen. Your degrees can be the same value. So remember, the degree is the highest, it's equal to the highest exponent of your variable. So degrees are, if they're the same, then there is a...
Your mic's a little bit messed up again.
I just, you know what? I'm wondering if when I, is it better now?
Yeah.
Yeah.
That was loud.
Sorry. It's probably because someone was falling asleep. You know what? I wonder if when I accidentally click my pen, if that offsets the mic somehow.
It seemed to happen on like every Zoom call I've ever had.
I apologize for that. I don't know how to fix that. Is it just like once or twice? It's not like the whole time, right?
Yeah, it's just kind of random when it happens.
All of a sudden, it'll just be like...
Yeah. Okay. So let me just kind of repeat what I was saying. You guys okay with the vertical asymptotes? Finding those? And then horizontal had to do with the degrees of the numerator denominator. You would look at the degree of the numerator. That's the highest exponent of your variable. Look at the degree of the denominator, so the highest exponent of the variable. If they're the same, then you do have a horizontal asymptote. And the horizontal asymptote is going to be at y equals a over b, where a is our leading coefficient of our numerator, and b is the leading coefficient of the denominator. So that's basically the value that the number in front of the variable with the highest power. We can show this by looking at long division of the polynomials. So again, horizontal asymptotes is the end behavior of your graph. If your end behavior of a graph is going to some y value, approaching one y value as it goes to infinity or negative infinity. And I'll come back to that in a second. If the degree of the denominator is larger, that means the denominator is growing at a faster rate than your numerator. And then there is also a horizontal asymptote, and it's going to be at y equals 0. And then the last case is when the degree of the numerator is larger. There's no horizontal asymptote. But if there's no horizontal asymptote, there's a slant So a slant or oblique asymptote exists. So look at the quotient. And remainder. To determine. Let's grab a page or a problem.
So slant and oblique are the same thing for in terms of asymptotes?
Slant, they usually, and sometimes books will use them interchangeably depending on which book. Slant can, I think, is talking about more of it being a line, where oblique it could be following a quadratic.
Okay, so they're pretty interchangeable, but it's just semantics.
Yeah, I think so.
Okay.
So let's say we're looking at, let me just pull one. An exercise, find the limit of each as x goes to infinity and negative infinity. If you wish, visualize your answer with, it says a graphing calculator, but we might be able to do that without. Actually, before we do that, let's just look at the limit as x is approaching 0. And so I'm giving you a different problem than what I was just reading, of 1 over x. So we just talked about rational functions and the graph of it. So if I was looking at f of x equals 1 over x, notice that it's undefined here when x is 0. So x can't be 0. Notice that that sets the denominator equal to 0, but not the numerator. And so we have a vertical asymptote. I'm going to do shorthand as x equals a at x equals 0. It's actually an equation of a line. The vertical line is always x equals that number. And then horizontal asymptote. Actually, before we do that, let's now look at the limit. So we can see that it's undefined here at x equals 0. Let's see what happens as we look at x coming to 0 on the left-hand side of 1 over x. So this is values that are x are smaller than 0 that we're plugging in. And let's just do it for a couple of values just to see what's going on. So this is something that's less than 0 but really close. So I know negative 1/10. If I plug that in for x, which is close to 0, I would get 1 over negative 1/10. Well, 1 over negative 1/10 is the same thing as, and we're multiplying what we're dividing by. So this is the same thing as negative 10. So same sort of reasoning if I did negative 1/100, which is even closer to 0 on the left. When I plug this into 1 over negative 1 over 100, this gives me negative 100. So I can see that this is going to be blowing up and getting bigger and bigger as I get closer and closer to 0 on the left. But notice that's going to negative infinity. And if I looked at the limit as x is approaching 0 on the right, of 1 over x. So this would be plugging in values which are positive, so 1/10. But when I look at 1 over 1/10, that gives me 10. 1 over 100 would give me 100. In this case, it's blowing up to positive infinity. So limit doesn't exist as x approaches 0. We have a vertical asymptote at x equals 0, but sometimes looking at left and right limits are helpful, so we know what's going on in the graph there. And then if we talked about those coming in, it's going downwards. Horizontal asymptote. If we look at f of x equals 1 over x, well, the degree of the numerator, that's just a constant. Degree of the numerator is actually 0. And the degree of the denominator is 1. And so the degree of the denominator is larger than the numerator. And so if that's the case, then it occurs at y equals 0. So that makes sense too, because if we're looking at the limit as x is approaching infinity of 1 over x, well, you're putting 1 over a huge number. 1 over a huge number is going closer and closer to 0. So this is looking like this. And the limit as x is approaching negative infinity of 1 over x, 1 over a huge, well, it's actually not huge, absolute value of a negative number that's going to negative infinity, that's going to be going to 0. So if we looked at the following now, so let's look at the limit as x is going to infinity of 2 over x minus 3. So we can think of this as 2 over a huge number, infinity minus 3. Well, 1 over, we just saw 1 over x. As x was going to infinity, was going to, that piece was going to 0. And so 2 over a huge number, this constant 2 over a huge number still, as x goes to infinity, is going to 0. And so basically, you have something that is going to equal 0 minus 3, or is equal to negative 3. I'm looking at the limit as x is approaching negative infinity of 2 over x minus 3. So 2 over negative infinity minus 3. So same idea. This 2 over something going to negative infinity is getting really big, but negative. This is going to go to 0, and so this is going to give us negative 3. So technically, this is showing that we have a horizontal asymptote. At y equals negative 3. What's happening as the limit as x approaches 0? So notice it's undefined here. So the limit as x is going to 0 of 2 over x minus 3. Well, and again, we need to look at left and right. It's undefined at 0. But if we look at the limit as x is approaching 0 on the left, you're plugging in negative numbers in here. that are going to get really, really small, and 2 over a really, really small number going to 0, this whole piece is going to be blowing up. And this is going to be blowing up to negative infinity. And so negative infinity minus just some constant is still going to go to negative infinity. But if we look at the limit as x goes to 0 on the right, you're plugging in positive numbers that are getting huge, and 2 over something that's getting huge here. That's going to, 2 over a small number, that's going to be going to positive infinity. Positive infinity minus 3 is still going to go to positive infinity. So we have a vertical asymptote at x equals 0. And just knowing these couple of things, we can kind of see what's going to happen with a graph. We had a y-intercept at -3. So down here at -3. The graph is going to hug it. We knew that as x is approaching 0 on the left, it's going downwards. Coming downwards. And as it's going to negative infinity, it's approaching this y equals -3. As x is approaching 0 on the right, it's shooting upwards. And as x is going to positive infinity, it's going to y equals -3. And I just looked at the time, so this is probably a good spot to stop. But notice, okay. No, I don't know. We're not done with this section, but we're just going to continue to look at rational functions and the limits of those. So if you forgot how to graph rational functions, hopefully this was like a quick review. I apologize, I was a little scattered today. And now my battery's running low. I didn't realize I didn't have it plugged in. Stop recording.
Well, hope you recover soon.